The normal distribution is part of probability distribution theory, and what we're really focused on in here is the CDF, the continuous distribution function. It follows this formula here, where ERF is the Gaussian error function of x, the actual value we want to evaluate, then mu being the mean, and sigma being the standard deviation. So, what is f of x? Well, f of x is the probability of a random value less than or equal to x occurring. Okay? So, if we evaluate the continuous distribution function, the CDF, of x, we then return, with the standard deviation of sigma and the mean of mu, we get the probability of a value less than or equal to x occurring. So what does that have to do with capability? Well, if f of x is the probability of a random value less than or equal to x occurring, then f of the lower spec limit is the probability of a dimension less than or equal to the lower spec limit occurring, the probability of x less than or equal to LSL. We also know that 1 minus f of USL is the probability of a dimension greater than or equal to, we also know that 1 minus f of USL is the probability of a dimension greater than USL. That's the probability of x is greater than USL. So, what can we do? Well, if we know that the probability of x being less than or equal to LSL is the probability of a failing value less than the lower spec limit. Anything less than your lower spec limit is a failing value. So now we know that this is the probability of failing below the spec limits. And the probability of x is greater than upper spec limit is the probability of failing on the upper side of our tolerance. So if we add those two probabilities together, we get the probability of an out of spec condition. Okay, so now we know that if the data is normally distributed, we can use the cumulative distribution function of the normal distribution to calculate the probability of getting an out of spec condition. So what we're going to now do is kind of sidestep a little bit and learn about the standard normal distribution. The standard normal distribution is a normal distribution with sigma 1, so standard deviation of 1, and mean or mu of 0. We use this because any normal distribution can be represented by the standard normal distribution using z-scores. It's a way of standardizing all of your values so that you really only need to care about one set of numbers. Really, generally, in most scenarios in engineering, we care about what's called 6 sigma. I'm sure you've heard of that. And that means that we really care. We want to be between -3 and +3 standard deviations of the mean. And a standard normal distribution, that means from -3 to 3. That's why we use the standard normal distribution. Pretty sweet, huh? So to use the standard normal distribution, instead of plugging x in, we would plug in z, where z is your z-score, calculated by x minus mu over the standard deviation. This allows you to standardize and basically pull out our x minus mu over standard deviation in the cumulative distribution function here, in the CDF here, and just have 1/2 times 1 plus the error function of z over square root of 2. It standardizes it, right? Okay, so what happens if we substitute our upper spec limit and our lower spec limit for x? Well, the z-score of the lower spec limit is LSL minus mu over sigma. We can plug that in, and we can get the probability of failing below the tolerance. If we plug in the upper spec limit, we can then use that z to retrieve the probability of failing above. Again, we know that those add together to the probability of an out-of-spec condition. Now, this kind of looks like we took a bunch of extra steps. We already had this. Why would we want to calculate out x minus mu over sigma? We already had this. Well, it's because this shifts everything. It transforms all of the data to centered around 0 with the standard deviation of 1.